Welcome back to Data Wrangling 101. Last time, we used the three different AIs to design a pharmaceutical cost optimization dashboard. Today, we are taking the next critical step, figuring out what data we actually need and how to get it. This is where the rubber meets the road. We'll go from our product requirements to a realistic data architecture that we can actually implement. I am going to show you a systematic approach using AI tools to research data availability, design around constraints, and generate test data. By the end of this video, you'll have a repeatable process for data discovery and architecture design that you can apply to your own projects. Alright, first step, I need to break down exactly what data our 3 MBP features require. I'm using Claude for this because it excels at structured analysis and can give me the granular detail I need. Let me ask Claude. I'm going to now paste in the product requirements document that we generated in the last video. Let's see what Claude says. Perfect. Let's look at this breakdown. So I see that the required data elements include drug master data, inventory data, consumption and usage data. Then we have reorder parameters, inventory management system, required data elements, is receiving data, location mapping and data quality requirements, and also the timelines. So real times are real time or maximum 15-minute delay. Completeness is 95% of data completeness for active SKUs. Accuracy 0 tolerance for stock level discrepancies less than 5% or greater than 5%. And standard location codes across all systems. This is for the first feature, critical SKU shortage alerts. Next, for the second one, for budget variance alerts with departmental down, we need budget data, purchase order data, inventory payment data. Then you have required cost allocation data, contract management, and so on and so forth. And also, we have unusual spending patterns as trigger thresholds and seasonal adjustment factors and such. And finally, for the third feature, one-click executive summary report, we need performance metrics, vendor performance data, operational KPIs, financial summary data, and report template requirements, automated content generation. Okay, great. All right, then the next thing it goes into is the data requirements, which is the temporal requirements such as real-time, daily updates, weekly and monthly. Then you have the data format requirements, data types and validation, and finally data security and compliance, which is making sure that the data meets privacy requirements by PIDA or PHEPA compliance for all data handling. Then you have master data management for SKUs and vendors, data governance aspects. This is a really comprehensive list of data requirements that will be required for completing the dashboard. Okay, let me copy this over, put it in my notes. All right. So I have captured that in my notes, and let's go to the next step. Now for the research phase, I am switching to ChatGPT because it's excellent at researching complex system landscapes and providing realistic assessments. This is exactly the kind of domain research ChatGPT handles well. So we are going to ask ChatGPT, let me put the data requirements that we got from Claude earlier, and let's see what ChatGPT says. Okay, so what hospital systems actually provide and limitations? So we typically available data are drug master data, inventory, usage consumptions, and cost. What are the limitations? Reserved or allocated inventory tracking may be partial or unavailable outside of ADC integration. Then automatic reorder parameters often require manual setup or external scheduling tools, and data quality control features such as timely updates, alerts, and validation rules vary widely among vendors. Then you have inventory management, typically available data, ERP financial systems, what's typically available, then data warehouses. It's doing a reality check against my requirements, and it is clearly stating what is available today or what is likely available today and what is not. And implementation notes, what needs bridging or add-ins, summary and way forward. So it's saying most of the required data elements do exist, but often across multiple systems that are not fully synchronized. Okay, let me add one more thing here. Let me say gathering this data. So for each of the features, based on the functionalities available in KNIME, it is telling me the feasibility of obtaining and using this data in the dashboard for the 3 features. It's also giving me a data integration strategy for KNIME. Okay, let me take this and the previous information, add it to my notes. Okay, so we have so far discovered that not all the data that we are looking for is easily available in the systems that are commonly used in hospitals. So let's now take this back to Claude and ask it to design a data architecture based on an ideal scenario for when all the data that we want is available, and for a realistic scenario for when only some of the data is available. So I'm going to ask Claude, and I will paste in the output that we got from ChatGPT. Okay, so it's given 2 data architectures. One is an ideal versus realistic. The ideal assumes that there is perfect integration, real-time data streams with 5-minute refresh, live API, and enterprise service bus, predictive analytics with ML algorithms, 99.5% accuracy, and 500K to 1 million implementation cost. Whereas a realistic scenario is daily, weekly batch file exports, since we are using KNIME for doing the building of the data app, then manual process of data quality, rule-based alerting instead of predictive analytics, and 95% accuracy with manual validation. Then the implementation cost for KNIME-based data app is saying around 50K to 150K. Okay, and then it also says KNIME specific benefits. Okay, let me copy this and we'll move on to the next step. Now, before I can commit to either architecture, I want technical validation. I'm using Gemini for this because it excels at identifying potential technical issues and performance bottlenecks. So let's ask Gemini for doing a technical feasibility study. Let me paste in the 2 data architectures here. I have to say that one of the beauties of these 3 AI systems is that it is able to take in data that may not be really beautifully formatted or structured and still make sense out of it and provide an output that is meaningful and actionable. So let's continue asking Gemini for a feasibility study. Okay, so it's done a evaluation of the ideal scenario, which it is calling as a dream state architecture, and saying technically this architecture is entirely feasible with modern data technologies, real-time API collections, but primarily, although the technical feasibility challenge isn't technology itself, but it's the implementation within healthcare, typical healthcare IT environments. Legacy systems. Many vendors still run old PIS and ERP systems that may not offer robust real-time APIs or modern integration capabilities. Vendor lock-in. Healthcare systems have long-standing contracts with specific vendors, limiting flexibility in adopting new technologies or integrating disparate systems. Data silos, data standardization, and then performance consideration. So implementation risk is high integration complexity. Integrating disparate legacy systems in real time is notoriously complex, requiring significant development effort, high cost, IT resource dependency, data governance and quality. And then realistic scenario, practical implementation is high feasibility within typical constraints. The architecture is highly feasible for most hospital environments. Batch processing, file transfers, and KNIME for staging and workflows are well understood and achievable within with existing IT resources. Then common practice. This approach aligns with how many organizations, especially in healthcare, initially tackle data integration challenges due to limitation of existing systems and budget. Then KNIME suitability. KNIME is excellent for this scenario, capable of handling file-based inputs and performing data validation and orchestrating workflows and generating reports. The other day I attended a webinar conducted by the folks at KNIME, and they said that the origins of KNIME was actually in life sciences. They started building the tool to help research scientists do visual low-code data science using the KNIME analytics platform. So I would think that a system like KNIME would find easy inroads into a hospital environment, because the researchers who would work in a hospital might already be familiar with KNIME. Okay, so let's see what are the implementation risks. Data staleness, manual, error prone, data quality burden, scalability concerns. Yeah, I agree. When working with file-based data transfer, scalability is a concern. Then limited insights, lack of granular real-time data limits, the depth and immediacy of insights. Okay, security and compliance, file transfer. While standard file permissions are mentioned, ensuring secure transfer and storage of sensitive healthcare data via network shared folders still requires careful configuration and monitoring to meet compliance requirements. And it is provided an evaluation of a recommended hybrid approach, and it says the hybrid approach is excellent. So we can start with a realistic 1 to 6 month low barrier entry, quick wins, build confidence, allows for iterative development and low user feedback, and provide ROI early. Proving ROI early is critical for securing future funding. Okay, this is excellent insights, and it's evaluating KNIME for its implementation feasibility. So it's showing strengths and challenges of KNIME. It is recommending that even though Claude recommended that we use an SQLite or an H2 staging database, it is recommending as the database grows that we look at using Postgres, SQL or MySQL, or even a basic SQL Server instance. Okay, that is great. Now that we have a feasibility study done by Gemini, I want to ask Gemini again, based on the technical validation, I am convinced that I should be sticking to a realistic data architecture than the ideal one. Now, based on this, the technical validation, I will now need detailed table structures that reflect actual hospital system outputs. So for that, I am going to ask Gemini the following. Pardon my poor spelling, but hopefully Gemini can understand what I am really trying to spell here. Amazing, amazing. So we have the various tables, the data that we need for building our three features in the dashboard, and it shows the table structure, the column names, the data type, and the constraints. So we are looking to generate synthetic data so that we can build a prototype of this dashboard, and this table structure will help us generate the synthetic data that we need. Let me copy this over into my notes. The final step, which is generating test data that matches our realistic table structures. I'm going back to ChatGPT because it's excellent at creating domain-specific synthetic data. Let me ask ChatGPT, let me put in the output that we got from Gemini here. ChatGPT is analyzing, which means it is thinking about the table data structures and trying to generate the sample data that I can use. That's amazing. So I think now let me download these files. Well, it's interesting that it has given me some data quality issues as well. There is some missing data here and there, like the location ID is missing. This kind of replicates the data quality issues that we might find in realistic hospital data. Now that I have the data sets, it will let me test how well KNIME architecture handles real-world data challenges. This is the foundation we need for part 3. Let me summarize the systematic approach we just used. 1. Detailed requirements analysis. Claude mapped specific data needs for each product. 2. Data availability research. ChatGPT researched what actually exists in hospital systems. And architecture design. Claude created practical solutions based on real constraints. And for technical validation, Gemini identified potential issues and confirmed feasibility. And 5. Test data generation. ChatGPT created realistic data sets for development. So now next time we are implementing this architecture in KNIME, we'll build workflows that can handle missing data, inconsistent formats, and other real-world challenges we have planned for. The key takeaway is systematic data discovery prevents surprises later. By researching constraints upfront and designing around them, we are building something that can actually work in production. If you're planning a data project, try this 5-step approach. It takes more time upfront but saves weeks of rework when you discover data limitations during development.